All right, welcome to the second part of our Chapter 9 discussion. There's to be a third one to come next week. And what I want to take a look at, kind of talking about today, is really reviewing and kind of putting a lot of things together that we've been talking about with Lewis structures and Vesper geometries, and starting to kind of look at a little bit more complex examples than what we've looked at so far. And also add in some things with kind of VSEPR geometries in terms of how we draw them. I think I started talking about that last time and didn't realize that was in part of the video I cut off of the last one to try and keep it from being really excessively long, which you'll see most of here in this portion instead. So we'll take a look at Vesper sketches, how we draw some of those geometries in 3 dimensions as I review kind of some Lewis structures and things with geometry. And then at the end, we'll take a look at introducing and talking about polarity. And with polarity, our main focus now will be looking at really our geometries here that we're taking a peek at, and those Vesper sketches will be really important to help us kind of look at where are what we call these dipoles that will help us figure out if molecules are polar or not. Which sounds like it's not that big of a deal, but turns out like polarity is actually going to be a huge deal in just about any chemistry class you ever take again in the future. Particularly things like organic and biochem, you'll see it a ton in those classes. And it's something that will show up heavily at the start of 1212 as well. So these, like I think I mentioned before, when we started all this stuff with Lewis structures, still among kind of the most important things we're going to see in all of 1211. So we definitely want to make sure we have a lot of these things down, which is why we're spending so much time on it here lecture-wise, but also in the lab. So what I want to start with is actually really just doing some examples to kind of review with. And so what I'm going to do is all of these examples that I have listed here, I'm going to work through kind of our normal process on the whiteboard, drawing the Lewis structure, taking a look at what is the Vesper geometry of everything then for the central atom, or in the last couple examples, atoms, plural. We'll take a look at those structures also. And then we'll also go into looking at then the polarity portion kind of after this. And we'll actually come back to each one of these examples and figure out the polarity for each of them as well. All right, oops. So before getting into polarity, reviewing these examples, I'll kind of slide this over so we can keep this in view of which ones we're going to take a look at. There you go. All right, so the first example we're going to be taking a look at is going to be phosphate, Po3 3-. So general steps, same things we're used to doing, right? If I want to take a look at where everything is in the periodic table, phosphorus is right below nitrogen on the periodic table, so it should have 5 valence electrons. Each oxygen has 6. We've seen these in previous examples, so hopefully that's not something new. I'm going to be going through that a little bit faster on most of these now, which means that just from the elements, I'd have a total of 23 electrons, but if I have a -3 charge, it means I really have 26 electrons to work with. And if I go to draw my structure, here if I go to put this together, 3 oxygens all bound to the phosphorus. And again, if I'm just doing the Lewis structure, where I put those bonds, not super important. I'll draw the actual Vesper sketch for this to show what it looks like in 3 dimensions here once we're done with the structure and get the geometries for it. So adding my electrons, I fill my outer octets. If I have 3 outer atoms, 8 each is 24. So I have 2 electrons left as a lone pair on the phosphorus. This thing has a -3 overall charge. Turns out all of those formal charges should be on those outer oxygens. Right? That would be our structure then for phosphate. And in terms of us having to add anything, it doesn't really do us any good to add double bonds. Like before when we saw sulfate, we added double bonds from some of the oxygens to the sulfur to get rid of some of the formal charges. But in this case, if we added a double bond here, we'd get rid of the negative formal charge in the oxygen, but then the negative charge would end up in the phosphorus instead. And so some little things that we haven't talked about yet, part of why I wanted to go through some of these different examples today, is if we have options of where to put a formal charge, usually if it's a negative formal charge, we want it on the most electronegative atom. If it's a positive charge, ideally we'd like it on the least electronegative, but sometimes that we don't always have the luxury for that. So in this case, oxygen is more electronegative than phosphorus, so we expect to leave that formal charge out there, and this would be kind of our best Lewis structure that we could really put together. Now, the next part of this that we talked about but last time is looking at geometries. Right? So let's start with the electron geometry for this molecule. So if we're looking at it, we want to count how many things are around our phosphorus. We have 3 bound atoms, and one lone pair. So 4 total things, 4 things around our atom. Electron geometry will always be tetrahedral. Now, molecular geometry, we do have a lone pair on that phosphorus, which means it's not tetrahedral. And instead, if we go back to that chart from the previous lecture, I'm not going to show the chart necessarily here, but this is where this geometry is coming from. If you look at, all right, what if I have 4 things around my central atom, 1 of them is a lone pair, 3 of them are bound atoms, my molecular geometry for that situation should be what we call a trigonal pyramidal. All right. Now, I mentioned I want to draw the 3-dimensional structure for this thing. So this is what we often refer to as our Vesper sketch. And I'm not going to write this label on all of them, but I will show the 3-dimensional drawing for all of these as we do them as well. And so anything that the electron geometry is tetrahedral for, I'll scroll this back down just so you can see that. The best way I think to usually start drawing this, if you have your central atom drawn first, is I like to draw an orientation that looks like this. Now, if you have Mr. Kruger or Dr. Herbert, it's possible that they may like to draw their wedges and dashed lines pointing the other direction, which would basically mean this wedge and dash would point this way, and the straight line would go to the right instead. That's the exact same thing. It's just spun 90 degrees. You know, we joke amongst ourselves who's right and who's wrong because it really doesn't matter. But this is the way I normally draw this in terms of general orientations of things. And so what I'm going to do from here then is for all of those sites, for a tetrahedral geometry, all of these spots are equal to each other, which means for the lone pair, it doesn't matter where you draw the lone pair. The lone pair can go in any one of these 4 spots, makes no difference. I think in case of matching our molecular geometry, it's probably easiest to put the lone pair on top and all of these oxygens on the bottom. And what this sketch is really representing, notice I have this wedge and I have this dashed line. The wedge basically means that this oxygen right here is actually coming not only down to the right a little bit, but out towards us. And the dashed line here represents that oxygen's going down to the right, but also back away from us, like into the page or into the board or the screen that you're looking at. And so this notation, kind of using these wedges and dashed lines, gives us a way now to try and draw 3-dimensional shapes on our 2D pages. And so this is going to be a really common notation. You're going to see it all the time, pretty much any future chemistry class. So something you want to be aware of and also be comfortable using as you kind of draw these structures. And like I said, the biggest thing, as soon as you realize you have a tetrahedral electron geometry, if you're thinking about things 3-dimensionally, you can draw this immediately and just not have any of the outer things filled in yet, and then just put in what you have on the outside. And it doesn't matter whether some of these are double bonds. If you have 4 total things, you just orient it this way. And since all the spots are equal, it doesn't really matter where you put things. So that would be what we call our Vesper sketch. And I'm going to put a little mark here for polarity. We're not going to talk about this yet, but we're going to come back to it. Right? Because I said we're going to do all of these examples. I'm going to come back to all of them and talk about their polarity at the end once we talk about what exactly that is and how we find it. Moving to our next example, we're going to take a look at nitrite, NO2-. So going through our same normal steps, getting Lewis structure, so valence electrons, nitrogen is 5, each oxygen is 6, the negative charge, so 18. It means that this thing's going to look pretty similar to the ozone example that we saw before. So nitrogen, our central atom, over 2 oxygens. And in terms of filling the outer octets, it's going to take 16 of our 18 electrons, which means there's a lone pair that gets to go to nitrogen with the 2 that are left. But when we look at that nitrogen doesn't have an octet, right? So we're not done with this Lewis structure yet. We do have to make a double bond. And this is a situation where we could make the double bond to the left oxygen or the right oxygen. I'm going to make it to the left one first. And I say first because really what we have here is resonance, right? We have 2 options that are equal in terms of which one is better than the other from a formal charge standpoint. So we do have resonance structures that we can draw both of for this case. Right? And if I want to be complete for this top structure in particular, this whole thing has a negative charge. So there's our negative formal charge in the single bound oxygen. We'd have the same on the bottom one as well. And we have the negative charge overall for the whole thing being in brackets. All right, geometry-wise, for our electron geometry, same as before, we just want to count how many things are around the nitrogen. So there's 2 bound atoms in 1 lone pair. Again, double bond doesn't matter. We don't count it twice. So there's 3 total things around our central atom. 3 total things around the central atom means we're going to have trigonal planar for the electron geometry. For the molecular geometry, now what we're going to do is look at how many lone pairs we have. And again, you can look at kind of your chart to help with this as well. If we're looking at our chart, 3 things around the central atom, 1 of them being a lone pair, 2 of them being bonds, should correspond to a bent geometry. And in particular, we're usually a little more picky on these. Most of us will usually include the bond angles of the starting geometry, which for trigonal planar is 120, because you can also get bent from a tetrahedral starting shape, which would be bent 109.5. So bent 120 for the molecular geometry there. And again, I'm going to leave a space down here. Oops, sorry, I'm going to do the Vesper sketch. And then I'm going to go ahead and leave a space for the polarity comment that we'll come back to. But for the Vesper sketch in this one, since this molecule, if it's trigonal planar, is already flat, we don't have to use any dashes or kind of wedges or anything like that. We can actually just draw it. We'd have nitrogen, and we can basically just draw things kind of in a trigonal planar shape. Right? I'll put the lone pair on top, the 2 oxygens down here, and that would be kind of our rough 3-dimensional orientation of things. And so if we were looking at the actual shape of just the atoms, that is kind of that bent shape between the oxygens and the nitrogen. And I'll leave a space here for polarity that we will come back to in a little bit. All right, next example. And feel free for any of these if you want to just like stop the video and just kind of try the examples that you see on the left-hand side and then play the video to see your answers. That's probably a good idea just to kind of check and practice a lot of these. But our next example, BRF4 minus. So first off, counting electrons, the bromine, like fluorine, they're both halogens, so they all have 7. So 5 times 7 is 35, plus 1 from the negative charge for the whole thing. That's 36 electrons total. We're going to have bromine as the central atom, with it being the first one listed. Then we'll have all of our fluorines. And we can fill those outer octets. Which is going to take up 32 electrons for those 4 octets, which means there's 4 electrons left, so bromine actually gets 2 lone pairs here. And since this whole thing does have a negative charge, it's the bromine that's actually going to have it in this case. Right, if we calculate the formal charge in that bromine, it is -1 there with the 4 bonds and the 2 lone pairs. Right, so that would be our Lewis structure. Bromine does have an expanded octet here, but that's totally fine because bromine's way down in the 4th row of the periodic table. All right, geometry-wise, electron geometry. So we have 2 lone pairs and 4 bonds total around our central atom. So 1, 2, 3, 4, 5, 6 total things overall. Means that our electron geometry is octahedral. And then since we do have 2 lone pairs on that central atom, if we start out octahedral and have 2 lone pairs, that's going to give us square planar for the molecular geometry. Now, Vesper sketch-wise, we're trying to draw this in 3 dimensions. Give us a little bit of room here. If we're drawing this thing in 3 dimensions, again, anything that's octahedral, you can start out drawing this way and then just add lone pairs as needed, depending on how many you have to add to different locations. But I usually end up drawing my 3-dimensional version of octahedral like this. And I think of it really just as kind of almost like a Cartesian coordinate system, right? Like an X, Y, Z axis all together that are perpendicular to each other. And I do use the wedges and the dashed lines to indicate that we have basically kind of coming out of and going into the page in that drawing. Now, in this case, we have 2 lone pairs. So it doesn't matter where we put the first one because all of these spots are equal really starting out. But wherever I put the first lone pair, I'm going to put it as the one that's coming out towards us. The second lone pair has to go opposite the first, right? Because lone pairs, remember what we said last time, they take up the most space around our central atom. So in general, our lone pairs are going to want to spread out as much as they can for this geometry. And so to spread out our lone pairs as much as possible, they will go opposite of each other, and that'll leave us with fluorines in the rest of our positions, which is why we really see this then end up as that square planar geometry that it's named, right? Because we have basically a square shape of our fluorines and everything is flat. It is a flat molecule in terms of just where the atoms are, not counting those lone pairs. I'll leave the space for clarity we can come back to. Next, take a look at SOF4. So now we're moving into things that have a few more atoms involved, right? So SOF4, we're going to draw this thing's Lewis structure. We do have 3 atoms this time. So picking this, again, the central atom should be the first one listed. It's the sulfur. It's our least electronegative element. And counting our total electrons, sulfur and oxygen are in the same column, so they each have 6. Each fluorine has 7, like we said in the last problem. So 28 from the fluorines, plus 16 more. We have a lot of electrons here, right? So what is that? I'm sorry, not 16 more from the sulfur and the oxygen, 12 more from the sulfur and the oxygen to go to 28. So we should have 40 electrons total. So we'll choose our sulfur. We have our 4 fluorines. And again, I'm not drawing this Lewis structure with any particular Vesper geometry in mind to start with, because that's what our Vesper sketch later is going to be for. If I fill all of these octets, what we're going to see is that for 5 octets, that is 40 electrons. Right? So that means that there are no electrons left for a lone pair in the sulfur. We look at the sulfur, it already has an expanded octet, so we don't have to do anything there. But the last thing that we want to consider is always formal charge. Right? So in this current version of the structure, this outer oxygen would have a negative formal charge, and the sulfur would have a positive formal charge with the current setup. And so what we can do to kind of help make the structure better and get rid of some of our formal charge is to actually go ahead and make a double bond from the sulfur to the oxygen. And I make it specifically there to get rid of the formal charge on each of them. Right? So by making that double bond, I get rid of the formal charge. Now sulfur's formal charge is 0, oxygen's formal charge is 0. Sulfur is totally fine expanding that octet. It already had an expanded octet. It's down in the 3rd row of the periodic table. That's fine. And so this would actually be our best structure, right? The double bond of the oxygen and then all single bonds to fluorines. And now for the next part of this, we can talk about geometries. So electron geometry. For our sulfur, we're just going to count how many things are around it. Well, we have 5 bound atoms, so 5 things total. This is going to be that Trigonal Bi-Pyramidal. So Trigonal Bi-Pyramidal for our electron geometry, and then our molecular geometry, if we had no lone pairs, now our geometry is still just the same. So Trigonal Bi-Pyramidal also for the molecular geometry. Now, Vesper sketch-wise, so this is one that's a little bit different, right? We now have the Trigonal Bi-Pyramidal geometry, which we haven't drawn yet. It is a 3-dimensional geometry. So to take a look at how we would draw that shape, the way I would normally go ahead and draw that is I would start with my central atom, which in this case is going to be my sulfur. And I usually draw 1 up, 1 straight down for my axial positions, 1 straight right, and then a wedge and a dash going to my left. And again, you may see this sometimes where the straight line goes left and your wedge and dash to the right. That's totally fine. I think these are kind of common ways, though, that we usually draw the Trigonal Bi-Pyramidal 3-dimensional shape or geometry. Now, there's one last detail here. We do remember for this geometry, and this is the only geometry this really, really matters, and it's kind of the same idea with lone pairs. Like we were picky about where the lone pairs always went. We always put the lone pairs in these equatorial spots because those were the spots that offered the most space. Well, it turns out if you have multiple bonds in a molecule, like what this one has, and then single bonds, the multiple bonds behave kind of similar to lone pairs because there's a lot more electrons in this double bond than there are in the other single bonds. So because of that, this double bond is going to want to take a spot that gives it the most space to kind of spread out because there's just the most electrons there pushing everything else away. So because of that, in this case, our oxygen is actually going to have to go in one of those equatorial positions. And then we'd have fluorines in all of our other spots. And that's kind of one of those things that once you get kind of a good feel and understanding, I think, of drawing like Lewis structures and this idea of why things go in these equatorial axial positions, if you truly understand that, you can kind of figure this part out based on kind of the double and single bonds. But it's definitely something that I wouldn't expect to just be inherently obvious or even necessarily too intuitive for people that have never really looked at this or thought of something similar. And so that would be kind of our Vesper sketch. And you will notice for most of these Vesper sketches, I haven't been drawing the multiple bonds usually in them. I'm really just trying to orient things in 3 dimensions. Sometimes you will see people like include all the other pieces like lone pairs, things like that. Usually for the Vesper sketch, I don't really care if you have those pieces there. I'm more just interested in the 3-dimensional geometry, right? And we should see the matching between whatever our electron and molecular geometries were to the actual then Vesper sketch that we see. All right. So I think that hits all of the major different electron geometries. I think the only one we haven't done an example of so far here is linear. I'm not going to do one necessarily for linear because really for linear, I think a Vesper sketch is kind of redundant because the Lewis structure pretty much just is the Vesper sketch. Things are directly opposite and that's it. There's nothing else to really talk about. But I do want to take a look at some larger molecules, ones that don't have just a singular central atom. And so something you're likely to see a lot of, particularly as you get to 1212 and definitely when you get to organic chemistry, not every molecule only has a single central atom. Particularly if you have molecules that have multiple carbons, or carbons and oxygens that might have things attached to them as well. It's very common that you're actually going to have kind of almost like a chain of atoms, like carbon chains or maybe carbons with oxygens involved in the chain or something that can pop up pretty frequently. And so what I want to talk about is kind of some of the notation that will give you clues to that. Right, so anytime like here we see CH3OH, this is methanol. Right, we saw this formula probably in most of our classes earlier this semester. And for methanol, there's a reason we write it CH3OH and not just CH4O. And that reason is basically to try and give structural information. So when we see this written as CH3OH, this hydrogen at the end, it's written separately from our other hydrogens to show that it's attached to the oxygen, not the carbon. Which means this doesn't have just one central atom, it actually has a couple, and so it is kind of a chain-like structure. And we're going to see this, like I said, a lot kind of going forward in 1212, and organic in particular, you'll see a lot of this. And almost all the time, it's going to involve carbons and hydrogens in some capacity that are going to then really have like, you'll have hydrogens listed here with this carbon, and then a carbon or a hydrogen here that's actually also attached to this carbon. And that's kind of the typical listing pattern to kind of show how things are connected. And we'll see this example again in the next one as well, or see the evidence of this in the next example. Now, in terms of drawing this Lewis structure with that information in mind then, we can still go through very similar steps. The only thing that's a little bit different is going to be that skeletal structure step, where if we know the carbon is bound to our oxygen and that oxygen is bound to a hydrogen, right? This is the hydrogen that's there at the end. The other 3 hydrogens are now attached to the carbon. This is our skeletal structure. And all that's left is adding extra electrons if we need them for lone pairs or if we have them for lone pairs, right? So if we count how many total valence electrons we'd have in the methanol to start with, carbon has 4, we have 4 hydrogens, so that's 8, plus 6 more from oxygen is 14. And if we looked at our structure, we have 2, 4, 6, 8, 10 right now, which means we have 4 left. Well, carbon already has 4 bonds, so it already has an octet, it doesn't need any more. Hydrogens, we never put lone pairs in the outer atoms anyway, so our only other option is oxygen, which if we look at it makes sense, right? Oxygen only has 4 electrons from those 2 bonds, so oxygen is going to get all of those remaining 4 electrons as 2 lone pairs, and now everything has an octet, and this is going to be our Lewis structure for this molecule. Everything has an octet, it's all happy, there's no formal charges anywhere either, so this is our final structure. Now, geometry-wise, we actually are going to have geometry of kind of different parts. Right? We can have the electron geometry for the carbon, as well as an electron geometry of the oxygen. Right? They're both kind of technically central atoms. And then we can also give molecular geometries around each. Right? So for the carbon, start here, we have 4 bound atoms to the carbon. So even though I've drawn it kind of in a square orientation, it really is tetrahedral. Right? And then for the oxygen, the geometry around the oxygen, we have 2 bound atoms and 2 lone pairs is also tetrahedral. And then for molecular geometries, we can do kind of the same, right? We can do molecular geometry of the carbon. Carbon has no lone pairs, which means its molecular geometry should be the same as the starting electron geometry it had, so it's also still tetrahedral. And then for our molecular geometry for the oxygen, since we have 2 lone pairs on our oxygen here, anytime we start out tetrahedral around something and have 2 lone pairs, that's going to give us a bent geometry. And in particular, it's going to be bent 109.5, right? Because that's kind of the standard tetrahedral bond angle to show that it is tetrahedral in nature to get to that bent shape, as opposed to the bent 120 that starts from trigonal planar. Now, Vesper sketch on this one. For a chain molecule, if we're going to draw what this thing looks like in 3 dimensions, probably the best starting place I think is going to be the carbon. That'll make it a little bit easier. And how I'm going to draw this, I'm going to start here drawing it this way. We'll draw it like that, starting out. And again, I've actually kind of flipped this from the way I standardly draw my tetrahedral shapes. That's okay. I think it'll be a little bit easier to show the oxygens from a space perspective here in the way I'm doing it. Then we'd have an oxygen over here that also is going to have one here, and then it's going to have a wedge and a dashed line. Right, so those would be the orientations around each of these 2 central atoms. And then really we're just going to put whatever we need to around them. And remember, since these are both tetrahedral, it doesn't matter what we put where. It makes 0 difference. For the carbon, it doesn't really matter because they're all hydrogens anyway. For the oxygen, we have 2 lone pairs and a hydrogen, but really all 3 of these spots are equal. If I rotate these around, this spot can rotate to that spot. So it really makes no difference where I put the hydrogen. Personally, I think it just looks a little bit better to put the hydrogen here, and then the lone pairs with the dash and the wedge. But that's, you could flip that up. You could put the hydrogen here and put the lone pair over there instead. That makes no difference. One of the things about single bonds, we don't go over a ton in general chemistry. It comes up a lot more in organic. Things can rotate around a single bond. So a single bond like this, things can rotate. So basically this hydrogen can be rotated over to here and everything's still the same. Nothing's changed in the molecule. All right, and then I'll leave one little space over here for what we'll come back to regarding polarity. But that's everything for now. We're going to do like Lewis structure, Vespers, and the kind of 3-dimensional drawing for methanol. One last example then, and this is also kind of an organic chain-like structure. This is going to be one of our polyatomic ions. Get my iPad to respond. Oh no. There it goes. Sorry about that. All right. There we go. So now we're going to take a look at acetate. And so when we go to draw this thing's Lewis structure, we want to kind of keep in mind, again, the structural pieces, kind of similar to what we saw before. We see this as CH3COO is kind of how this is often written. Maybe CH3CO2 is sometimes also a common formula for this. And the CO2 part might actually be a little bit more structurally informative even than kind of the way it's listed here. Because the 2 oxygens are not going to be attached to each other in this case. That's not something that I would expect people to just kind of standardly know offhand, having never really probably seen or had to draw structures of this type before. And so to put this thing's skeletal structure together, we'd have our initial carbon that's again going to have 3 hydrogens, but now it's bound to this carbon. Right? So we have a carbon-carbon chain that's starting. And then I have these 2 oxygens. And really, oxygens being bound to each other are really rare. So usually if you see like a COO minus like this, really what that is you actually have 2 oxygens both attached to that same carbon. And then again, our 3 hydrogens on the first carbon that I drew on the left side. So this would actually be kind of our starting skeletal structure. And then we can go through that process of putting in all of our electrons. Right? So here we'd have 3 from our hydrogens, a 4th one from the negative charge, 2 more carbons that have 4 each. That's a total of 12 so far. 2 oxygens are 12 more. So we actually have 24 electrons to put in here. Well, here's 2, 4, 6, 8, 10, 12. If I have 12 electrons left, that's 6 total lone pairs, which means 3 each on each of those outer oxygens. or really we can consider them outer oxygens and just put all the lone pairs on there. Probably is actually maybe the slightly better way of thinking about it. And so we can fill those outer octets. That at this point we've used all 24 electrons that the structure really had to start with. So we don't have any left to add. But when we look at it, there is something that's still wrong with the structure, right? We're not done because this carbon in particular only has 3 bonds and no lone pairs. So this thing doesn't have an octet yet. So if this carbon doesn't have an octet, the only way we can give it an octet is making a multiple bond. This carbon over here has no lone pairs, so it can't make the multiple bond, so it has to be one of the oxygens. And so we are going to get a double bond here. But if we look here, I put the double bond to the top oxygen, but I could have also put it on the bottom oxygen, right? I don't know which one is correct, because really this is an example then again of resonance. And so I am going to have a formal charge on the bottom oxygen the way I've drawn this. This whole thing's an ion, right? So brackets. But I do have resonance going on here. I'll draw this second one a little bit more condensed. That basically just has the oxygen carbon double bond on the bottom instead. Right? And I'm not going to go through the full details again on the second version, but just to show the double bond is moving. Right? So we do have resonance here in acetate. It's part of what actually makes acetate a very stable polyatomic ion. And if you think about a lot of our polyatomic ions when you're drawing their Lewis structure, there's a good number of them that do have resonance. And part of the reason that those ions then are so common is this resonance actually helps to kind of stabilize that charge that particular ion has. And we're not going to do probably too much more with that really in 1211, but we will come back to that more in 1212 and organic a lot as well. And we'll see that resonance plays a key role in a lot of different things. Particularly in 1212, we'll start relating to things like acid strength. Right? Acetic acid is not a strong acid, it is a weak acid, but there are some acid strength patterns that we can kind of come back and relate to these types of structures. And so there are things that we can kind of get into with that, like I said, we'll eventually get to, but not really in this class, not right now. Now, the other pieces for this one then, if we want to answer kind of some of our other things that are going on, we can do things like talk about our geometry on, I'm going to say, let's do electron geometry of the left carbon and then the right carbon. We can do kind of each of these. The oxygens are kind of the outer atoms. They're not really central, so I'm going to look at, again, mainly the central atoms of this. So I have one carbon that has 4 things around it. So the left carbon has 4 things, so just like before, tetrahedral. And if I wanted to do the molecular geometry of that carbon as well, that's also tetrahedral because there's no lone pairs there. And now for my electron geometries, sorry, I'm getting ahead of myself here. My electron geometry on the right carbon, this carbon only has 3 atoms attached to it. Right? Remember, it has 4 bonds, but it's all about how many atoms it's attached to. So 3 attached atoms, no lone pairs, means that its geometry is trigonal planar. And its molecular geometry is also trigonal planar because there's no lone pairs on that carbon. Right, so those would be kind of our geometries around the main central atoms here. Again, we're going to come back to the polarity part. I'm going to put polarity down here with a question mark. It's a good example for us to talk about that on. And this is actually probably a good example that we'll come back to for a couple other things in the next lecture as well, as we start talking more about valence bond theory also. But for now, what I want to do before I do any other examples of anything, what I'd like to do is actually talk about this idea of polarity and then just come back to each of these examples individually and talk about how do we figure out if each of these molecules are polar. And so I want to take a look at what that process involves. So we're going to jump back into our slides here for a little bit first, and then we'll go ahead and come back to those examples. So when we talk about polarity, one thing I do want to kind of emphasize, right now we've talked about how a bond can be polar. Right? This is what we talked about in one of our previous lectures, and we talked about how if 2 atoms have different electronegativities, the bond that they make can actually be a polar covalent bond, depending on how close those electronegativities are or how different they are. But what we're interested in now is really figuring out whether or not our molecules are polar. So it's kind of a more complex issue because most of our Lewis structures that we draw, there are going to be polar bonds. Like it's very common that we're going to have polar bonds because if you have 2 elements that are not the same element, probably more often than not, if it's making a Lewis structure where like it's already got covalent bonding, there's a good chance it's probably a polar bond. There are exceptions to this, carbon and hydrogen always being the big one that always stands out. Carbon-hydrogen bonds are nonpolar, but a lot of other times, like if the two elements are different, probably assume it's a polar bond unless we actually have the electronegativity values there for us to look at to be able to tell that they're going to have the same electronegativities. Now, in terms of then applying all of this to the molecule to figure out if that molecule is going to be polar, part of the reason we just spent all these times talking about Vesper geometries is we really need to know the shape of the molecule. Because what we're actually going to be doing is really taking a look at the molecule's shape and figuring out for all of the polar bonds that are in the molecule, how are they oriented relative to one another? And are they oriented in a way where what we call these dipoles that are going to be present in each bond, if those are going to be lined up in a way that they cancel out or not? That's going to be kind of a general shortened version of kind of what we're going to be trying to do or look at for a lot of these shapes to figure out if something's polar. Now, how we go about actually trying to do that, there's going to be a couple different things that we want to always keep in mind. So I'm going to start out with kind of some general ideas to keep in mind when you first start looking at a molecule to figure out if it's polar or not. Then we'll go through like what the process actually looks like for the examples that we have to go through that process on. And then at the end, I'll kind of get into some different patterns that we might be able to kind of shortcut some things into that will actually help speed up the process for figuring out whether things are polar or not. Because not only do we want to right now be able to figure out is a molecule polar or nonpolar, eventually you want to be able to look at a molecule and almost immediately figure out is it polar or nonpolar without having to take a ton of time to figure out that information. And so there are some patterns and other things that we can look at that can help with that that we'll talk about as well. So some of the first things starting off, just because you do have polar bonds does not mean that the molecule itself will be polar. In fact, there's lots of examples. We'll look at a couple here today that there's lots of polar bonds, but the molecule itself might actually be nonpolar. There are ways for that to happen. Now, the opposite of this, though, is actually always true. If all you have is nonpolar bonds, the molecule will always be nonpolar. So instances where all of the elements are the same elements, like ozone or O2 or something of that sort, those are going to be nonpolar because all the elements have the same electronegativity. So the bonds themselves are nonpolar to start, so the molecules usually end up being nonpolar. Now, the other side of that too, if you have like carbon-hydrogen, like a lot of hydrocarbons or organic molecules, like pretty much any organic molecule that's just carbon and hydrogen is always nonpolar because they have just nonpolar bonds to start with. And that's a big foundation really of organic chemistry is the fact that carbon-hydrogen bonds are nonpolar. Now, if we have polar bonds, kind of the general process that we're going to use to try and really see if what we call these dipoles cancel out or not is going to be something called vector addition. And so I'm going to demonstrate kind of just some generic examples of this in the next slide. Then we'll look at applying this to a couple molecules to see it kind of applied in the molecules as well. And then we'll go into looking at kind of further examples of kind of looking at new molecules, kind of going through this potential process to figure out, like, do we have a polar molecule or a nonpolar molecule before kind of getting, like I said, some patterns hopefully that we'll start recognizing that'll make things easier. So vector addition. How vector addition generally works. If we have two vectors, I usually like to use something called a tip-to-tail method because this can work whether we have two vectors or if we have 6, it doesn't matter. We can use and follow kind of the same general process and we're going to get the same result at the end. And so here's where we have an example. We have two different vectors. They're both pointing in the exact same direction. They have the same magnitude. So basically the way this tip-to-tail method works, if you start drawing one vector, where that vector ends, start drawing the next. So if I started here as a general starting spot, there's vector 1. The vector I want to add to it goes to here. So my overall, what we call net vector, or sometimes you hear it called a resultant vector, starts here and ends over here, which is then what we see over here. And you see the R here represents what's called that resultant vector, or we will refer to that usually as a net dipole if there is an overall kind of vector that's left at the end of adding things together. If we have things that go opposite directions, we can still do the same process. Right, so here we have a vector A that, if this is our general starting point right here, A goes 5 units to the left, B goes 10 units to the right. So from here, I'm now going to go back to where I started and then an additional 5 to the right, which is why my resultant vector is 5 units to the right, basically for that vector. So that's kind of the very generic aspect of how that tip-to-tail method works. I'm going to show some other shapes and geometries of kind of how this works as well. So here is an example. We have 3 vectors pointing in kind of really a trigonal planar geometry. So you can actually think of this example right here as kind of looking at BF3 in terms of trying to figure out if it's polar. If we have dipoles pointing towards where the atoms would be, which is going to be the common direction they usually point, because remember your least electronegative element's in the middle. We usually draw what we call dipoles, really as vectors or arrows pointing to the more electronegative atoms, which are usually just the outside ones. So in this case, if I have these three vectors that I want to add, I can start by drawing vector A. So vector A, if this is our origin, vector A goes up to the left. Where this one ends, I can start drawing vector B. So from here, I'm going to go up to the right for B, which is going to end there. So A plus B gives me this red vector right here. And now I can add this red vector, this resultant, to C. Well, if this again is my general starting point, I'm up here where B ended, I can start drawing C, which goes straight down. Notice I'm going to get right back where I started. Right? This resultant and C are exactly opposite of each other, the same size, opposite directions. So they're going to cancel, which means once I basically go one vector, two vectors, three vectors, if I end up where I started, that means there's no what we call net dipole in the case of our dipoles for our polar molecules. So if there is no net dipole for our molecules, that means they are nonpolar. Anything that has a net dipole, so basically all these vectors, if they don't cancel out, that's going to be a polar molecule instead. And we're going to see that all of our general kind of electron geometry shapes are all very symmetric, that if you have the same element and all the spots of one of those electron geometries, whether it's tetrahedral, trigonal bipyramidal, trigonal planar, or octahedral, if all the outer atoms are identical to each other and there's no lone pairs in that central atom, like your molecule will always be nonpolar, always, because they're all going to have these symmetric geometries that those electron geometries have, where basically all of these vectors are going to cancel out. This example right here shows for trigonal planar that anything that's trigonal planar, as long as all of the outer atoms are identical to each other, anything with a trigonal planar geometry with the outer atoms the same is nonpolar, because these dipoles should all cancel. So that's kind of the generics of it. We won't have to worry about too many things being kind of crazy like what this one looks like, right? So here we can still do the same process, right? If I start here, A goes up to my left a little bit, B goes out a long way to the right, and up a little bit. So where A ends, I start drawing B. That's how I get to here. And now if C goes down to the right, I can imagine going down to the right a little bit. And then if I start here and end somewhere over here, that's this kind of purple vector at the end for our final kind of resultant from doing that. Luckily, ours won't usually be this complicated, although I will say we do have some three-dimensional geometries, which might make things seem a little weird at first, but actually aren't all that bad once we start seeing a couple examples. So I'm going to show some examples for this, but I will highlight we have to have the correct Lewis structures, and we kind of have to understand our three-dimensional geometric shapes first to really be able to even look at polarity or do any of this vector addition. Because if you've messed up the Lewis structure or messed up the geometry, you probably haven't drawn things with the appropriate kind of relation to each other in 3D space. And so trying to add up or cancel dipoles doesn't really matter if your starting shape is already wrong. And so that's why we harp on all that stuff with Lewis structures and drawing those Vesper geometries or knowing those Vesper geometries, because it's really important to a lot of other applications. Polarity is going to have a lot of applications down the road, so we really want to understand the shapes and being able to look at the shapes to figure out what we call this polarity. So what I want to show here, I apologize for it's turned out pretty blurry for some reason, but what I want to show here in this image is really just a couple of very similar compounds, right? So here I have CCl4. This DPM abbreviation you see under each of these different molecules, this DPM is something called, it really stands for the dipole moment. The number is basically the separation of positive and negative charge throughout the molecule. So if I look at CCl4, this first example down at the bottom that I'm going to look at, for this molecule, since all of my chlorines are identical, and really they don't show it, but carbon here has no lone pairs. This is basically a tetrahedral geometry, although it's maybe hard to see three-dimensionally for some of these ones that are on the bottom. But it's a three-dimensional geometry, but if I have dipoles pointing towards all of these chlorines, tetrahedral geometries are symmetric in a way that all those dipoles will cancel. And we see that here by the fact that there's zero dipole moment. That means there is no positive and negative end to the molecule. But if I change any of those outer atoms, so for instance, if I go to, here I have CHCl3, so in this molecule, I basically took this chlorine and made it a hydrogen. But what that did is now carbon-hydrogen bonds are nonpolar, so there's no dipole pointing out to where this chlorine was, which means if there's no dipole pointing in this direction, the overall molecule has some net dipole pointing up here that didn't get canceled, that's going to be pointing the opposite direction of where the hydrogen is. And so that's what this little plus to an arrow sign symbol, this little yellow symbol, It represents what we call these dipole moments, and I'm going to draw some of these on my whiteboard so you can see kind of, again, a little bit more of a how do we draw this on paper as opposed to just looking at images like this one to see this more. But that's really what I'm trying to kind of display here is the fact that as soon as we get something on the outside that's different, it can be a different atom of a different element, or it can be even just a lone pair. It's going to throw off all of the symmetry so that dipoles don't usually cancel. So CCl4 is nonpolar, has no dipole moment because everything on the outside is the same and there's no lone pairs. CHCl3 is polar because the one hydrogen breaks up the symmetry of the outer atoms. CH2Cl2, it's also polar. We have two hydrogens, but again, this is where three-dimensional stuff matters. If you just drew this in kind of a square shape around a carbon on your page and thought, oh, it's just a flat square planar shape, that's the wrong geometry, and you're going to think it might potentially be nonpolar if you put the hydrogens and chlorines opposite. But in reality, they're kind of at bent angles from each other, and so they're not opposite, and so there is an overall dipole here that doesn't cancel out, so this compound ends up polar. CHCl, or CH3Cl, right, kind of still the same idea. If we have three hydrogens and then one chlorine, the one that's different has this dipole that's different from everything else, and so it's going to break up the symmetry and cause it to be a polar molecule. And so those are going to be a lot of the pattern kind of based parts that we'll be able to start looking at in further examples too. If we have kind of our broken up symmetry in a way that all the atoms on the outside aren't the same, or if there's a bunch of lone pairs, or just any lone pairs really on the central atom, those things usually cause molecules to be polar. And so we're going to look at, again, just examples of kind of going through this in some different ways. So let's take a look at just an example here then. Let's take a look at SF4 and we want to figure out, is this molecule going to be polar or not? And look at how do we actually go through this process. Well, the first thing is figuring out a Lewis structure, right? And so I'm going to kind of put up the Lewis structure over here on the right. It turns out that for this thing's Lewis structure, it has single bonds, and this is actually more of a Vesper sketch. So if I want to draw the Lewis structure, I'll just draw the Lewis structure here quick so we can see it over here as well. So if I want to draw this thing's Lewis structure for SF4, if I count my total valence electrons, each fluorine has 7, right? So 28 plus 6 from sulfur is 34. So when I go to draw this thing's Lewis structure, I may have drawn this kind of I'll draw it this way actually. This is my normal way of drawing it. There is going to be a lone pair on the sulfur once we fill all the outer lone pairs, because filling all the outer lone pairs will take 32 electrons, which means there are 2 left for that central sulfur. It is an expanded octet in the sulfur, but it's in the third row. It's fine with that. So this would be our Lewis structure, and I have actually kind of already drawn it a little bit in a three-dimensional orientation. Right? You saw I had a line here originally. This is a trigonal bi-pyramidal geometry because there's 5 total things around that sulfur. And so by having those 5 things, that's the shape that we actually see here. And so now we'll go back to the slides because I think the slide has slightly better visual to maybe see some of this information from. So now if I'm looking at this, and it's the same shape I just drew, just kind of, again, spun 90 degrees. Probably Dr. Herbert and Mr. Crew can get a good laugh out of that since they say I draw mine backwards. But if we're looking at this shape, we can draw dipoles from the sulfur to all of the fluorines on the outside, right? And the arrows are all pointing to the fluorines on the outside because fluorine's more electronegative, right? We're always pointing the arrows towards the more electronegative elements. And these little delta symbols, these are partial charges. So all these outer fluorines are going to feel like partial negative charge because they are more electronegative. They're pulling the electrons closer to themselves in that bond. And the sulfur, as a result, since all the electrons are getting pulled away from it, the sulfur is going to feel a partial positive charge. And now what we're going to do is look for the entire molecule. If I try to take all of these dipoles and add them all together, I have one going straight up and one going straight down. Well, those are exactly opposite, so they're going to cancel. They're not going to do anything. Over here, I have one that's coming kind of to the right and out towards us. And then I also have one going to the right and kind of back away from us. Well, the back away from us and the kind of out towards us parts are going to cancel. But if we add those two together, they're still on the whole going to point straight to the right. And because I have a lone pair over here, there's no other dipole going back to the left to cancel these two out. And so the end result is because of the lone pair being here taking up space, it breaks up the symmetry of all of our bonds. It means that we do have this net dipole overall that points to the right in this molecule. And again, I can kind of try and show that by drawing. So if I zoom this back out to this part, if I wanted to try and draw all those dipoles, I can show the dipoles the same way they had them here for my version. And if I just pick a starting point, I can basically say, okay, here's my first dipole, go straight up. So I'm going to go straight up from where I started. My second one goes straight down. I'm going to go right back to where I started. And then my next one's going to go kind of away from us to the left. So I'm going to draw us at a slight angle back to the left. And then where that one ends, I start drawing the next one, which my last one is this dipole, going kind of towards us to the right, so at a little of an angle to the right. And if this was my starting point and this was my end, right, I'm going to have some net dipole for the way I drew it going to the left. But that mine goes to the left because my fluorines were on the left, and the slide, the fluorines were on the right, so the dipole pointed to the right. But either way, regardless of how I started my starting orientation, I have a net dipole, and that's the most important part, right? Because any molecule that has a net dipole, so has a net dipole, that means this molecule is polar. And that's what I'll be going back to then for all of our previous examples. I am going to go back and take a look at, can we figure out if these things are polar or not? A couple of things that I'm going to show first, because I also want to show and talk about some of the patterns. I've talked about like adding these kind of vectors and shown a couple quick examples. I'll show more. But I also want to talk about the patterns too, as we're kind of doing this, because I think it will help the patterns to make more sense. Right? I've been talking about a lot of symmetry so far. So molecules that don't have any lone pairs on the central atom, excuse me, and all of the outer atoms are identical, are always nonpolar. So all of these examples right here, like BF3, CCl4, PF5, SF6, all of these, the central atom has no lone pairs and the outer atoms are the same. Right? For SF4, and this is why Lewis structures are important and why you want to draw them out every time for these examples, SF4 looks a lot like CCl4 from the formula, but when you draw the structure, this has no lone pairs in the carbon. Sulfur does have a lone pair, which is why SF4 is polar and CCl4 is not. And so that's why these Lewis structures and things we've been doing are important. And a lot of times, at least starting out, until you get really used to them and more comfortable drawing them, you're probably going to want to draw them each time to help figure out if things are polar or not. Now, molecules with lone pairs, here in the statement it says that they are polar. I'll kind of clarify that maybe a little bit and say that they are usually polar. More often than not, like maybe 90–95% of the time, if you have lone pairs on the central atom, that molecule is probably polar. But there are a couple exceptions, and so I do want to highlight a couple of the exceptions. And actually, I think my first example here, CO2, is probably not even an exception because there's still no lone pairs in the carbon. But it is pointing out the geometries, right? So the two geometries that can sometimes have lone pairs on the central atom and still be nonpolar with polar bonds are going to be XEF2 and XEF4 for the examples, but really those are just linear and square planar geometries. So XEF2, if we draw a Lewis structure and find its geometry, it has a linear molecular geometry, which is why this is actually a nonpolar molecule. XEF4 is also nonpolar because it has a square planar molecular geometry. So these two geometries in particular do have the ability to be nonpolar, even though there's lone pairs on that central atom. Otherwise, if it's not one of these two geometries, if there's lone pairs in the central atom, it's going to be a polar molecule, as long as you have the polar bonds to start with. And so this is kind of a more pattern-based approach to and just kind of way of thinking about examples that may make it easier than always drawing out the dipoles and seeing like, do they cancel out or not. And so what I'm going to do now here is I got one more slide of a couple images I'll show quick. But what I'm going to do is go through all those examples on kind of that whiteboard setup that we've looked at so far for Lewis and Vesper structures. And then we'll go through all of those and really look at kind of both ways of looking at things from a polarity perspective. Real quick though, before we do that, I do want to highlight one thing that you will sometimes see from some different sources. This is actually from our previous textbook that we used. I don't think it's our current one, but I just want to kind of get rid of some confusion that comes up with this a lot of the time. Really, I think from everyone that I've talked to in our department and others, I don't ever draw a dipole like this as part of a lone pair. So like these examples that draw dipoles with the lone pairs, I kind of hate those examples, honestly, myself, because I just don't think that's useful. Usually when we talk about dipoles are only the bonds. That's it. So when we were doing stuff for our class, you should really only draw dipoles for the bonds. Those are the dipoles that we're adding up to actually see whether our molecule will end up polar or not. The lone pairs themselves, there is electron density in the lone pairs, but the lone pairs themselves do not have a dipole. And unfortunately, there's a lot of images like this one that are out there, but this is not a very good representation of this. So I would ignore, like I said, ignore any dipoles drawn with the lone pairs like this. I just think that makes things overly confusing. Draw the dipoles for the bonds, and those are what you're trying to cancel out. And if they don't cancel out, then it's a polar molecule. With lone pairs don't ever have a dipole. And like I said, we'll see that on the examples that I'm about to go to now. Then. All right, so we're going to jump back to our whiteboard, and I'm going to go all the way back to what we started with today. So our first example that we started with, all the way back at the beginning, was phosphite Po3 3-. And this is where those Vesper sketches are now really nice, right? Because I can now use this Vesper sketch to kind of look at my dipoles and see what's going to cancel. And so what I was just saying, our lone pair doesn't really do anything in terms of dipoles. So what I'm going to look at is just the bonds. Right? We have phosphorus and oxygen are different elements. So like I said, if they're different elements, kind of assume it's a polar bond unless we tell you otherwise. The only two different elements you should know for sure are nonpolar bonds or carbon-hydrogen bonds. If you know that part, that should be all you need for right now. We can kind of add to that as we go. There are some other electronegativity trends that sometimes you can use, but for right now, I think that's usually pretty sufficient in how we look at things. So different elements, we're going to get a polar covalent bond here. Oxygen's the more electronegative one, so that means what I'm going to do is I'm going to draw a dipole as an arrow pointing towards the oxygen for each of these bonds. And notice for all of these, if I'm looking at this in 3 dimensions, I have one that's going down to the left, one that's coming down slightly to the right and towards us, one that's going down a little bit and to the right and away from us. If I want to add all 3 of these together, if I pick a starting point, say that's my starting point, I'm going to go down to the left. I have one that's kind of coming down to the right and at us, one that's going down to the right and kind of away from us, so a slightly different angle. But regardless, exactly how I draw these last 2 as far as coming in or out of the board, what's going to happen is notice where we started versus where we ended, they're not really close to each other. Right? It's very obvious that we have a net dipole going down. Because basically just going from where we started to where we ended. And actually here, let me see if I can grab a different color here. Right? There would be our net dipole going down from where we started down to where we ended. So if we do have a net dipole, because we have a net dipole, that means this thing's going to be polar. And that's, again, kind of the general process of trying to draw these things to figure that out. In some ways, once you have the Lewis structure, the kind of more pattern-based approach is, all right, I drew my Lewis structure, all my outer atoms are the same, but I have a lone pair. So I have a lone pair in the central atom. I look at my molecular geometry, it was trigonal pyramidal. That's not one of the linear square planar exceptions that we mentioned. So if I have a lone pair, it's not linear, it's not square planar, I have polar bonds, so it should be a polar molecule. And that is what we see if we try to add those dipoles. And so we should always see kind of that more pattern-based way of trying to think about the lone pairs and the symmetry in comparison to actually drawing the dipoles. They should always match. We shouldn't be getting different results from one compared to the other. All right, so let's look at the next example. Nitrite, NO2-. So over here, I drew my molecule this way, right? And this is why the Vesper sketch is important, because this molecule is not linear, right? We said in the molecular geometry over here it's bent. That's why we drew it like this for our Vesper sketch. So that makes it a lot easier to tell for our 2 dipoles, right? They should be pointing towards the oxygens. And really, just as a good rule of thumb, your dipoles for each of your bonds, if there's a dipole, it's always pointing outward unless the outer unless the outer atom is a hydrogen. If it's hydrogen on the outsides, then usually the dipoles will point towards the central atom instead. But that's pretty much the only scenario where we usually see that. So in this case, there's my 2 dipoles. I want to add those together. So let me pick a starting point. Say here, I have one that's going down to the left. I have a second one that's going down to the right. But what that means is, at the end of this, I do have this resultant vector that's going down. Right? That's my net vector. So I do have a net dipole, which means that my molecule is then a polar molecule. And so again, that's kind of our general process. And in the pattern-based approach, I have a lone pair in my central atom. Molecular geometry is not linear or square planar. Should be polar as long as the bonds are polar, and they are. And so we get a polar molecule. All right, next example, BRF4. All right, so for this one, I want to go through the same process that we've been doing. Let's start with the Vesper sketch. Right, this was the geometry that we assigned. It is square planar here. So if I want to draw my dipoles, I have one that's going to go straight up towards the fluorine, one going straight down towards the fluorine, one straight to the right, and one straight to the left. Well, if I go to add those up, this is my starting point. If I have one that's going up, next one's going straight down, right back where I started, one going to the right, and the next one going right back to the left. Notice I end up right where I started. Right? So at the end of this, I have no net dipole.
And anytime we have no net dipole, this is when we are nonpolar. Right? Basically, the dipoles here are exactly opposite of each other. And from a pattern-based approach that we were saying before, I have lone pairs in the central atom, but my molecule is square planar. And so if it is square planar, now I have the possibility that all my dipoles are exactly opposite, which is what we see here. They're all the same elements on those positions, so all the dipoles do cancel, and I get a nonpolar molecule out of this. And one other thing I will note, you'll notice all these examples we've looked at are anions. And again, so they do have negative formal charges, and they do have negative partial charges and positive partial charges as well. But to be polar, you need really a negative and a positive end to the molecule. So like a buildup of partial positive charge on one side and a partial negative charge on the other. In anything like this, all of your partial negative charge is all on the outside. There's no like positive and negative end anywhere, and so that's why it's not considered polar. It's considered nonpolar then instead because of that. All right, move on to our next example then. Let's take a look at SOF4. And again, I'm going to kind of the Vesper sketches for all of these because it's the 3D shape that really is critical. So if this is our three-dimensional shape, I want to draw all my dipoles. Right? I have a fluorine dipole going up, another one going down. And now here's the one thing that's a little bit different. Right? I have an oxygen and then two fluorines. Well, in terms of the dipoles that we draw, the stronger the dipole, or basically the stronger dipole happens when the electronegativity difference between elements is bigger. So fluorine's more electronegative than oxygen, so there's going to be bigger dipoles pointing in this direction than there are this way for the oxygen, because fluorine's more electronegative than sulfur by basically a larger amount, because fluorine's more electronegative than the oxygen is. So we're going to get two pretty big arrows going kind of to the left and at us and away from us, and kind of a little tiny arrow in comparison anyway. Probably isn't quite this different, but I just want to make sure that it's kind of evident what's going on here for my drawing. So now when I go to put everything together, again, I can pick my starting point. I have one dipole here that's going to go up, so I can draw a dipole going up. Next dipole, I can say here, is going right back down where I started. Then I have a dipole that's going kind of to the left and away from us, so I'm going to slant it slightly. That's not the greatest arrow. There we go. And then I have another one that's going to the left and kind of out towards us. That'll get us back kind of in line. And then I have one dipole that's going straight to the right, but it's only a little bit. Right? So I only go back a little bit. So this was my starting point. Here was my end. Right? So I do have an overall net dipole that's going to be present, which means that at the end of all of this, my molecule is polar. Right? So for my polarity, this is a polar molecule. Now, from a more pattern-based standpoint, it's almost faster to recognize that this should be polar. I have a central atom that has no lone pairs, but my outer atoms are not all the same. And pretty much as soon as that happens, if your outer atoms are not all the same, probably the only time this might be able to get away with still being nonpolar is if it's square planar. Like if I go back up for a second to this example, like if these had both been chlorines instead of fluorines that are different, so we'd have like fluorines here and here and chlorines here and here, that could still be nonpolar because the dipoles are still opposite to cancel, but that's kind of the only time that could ever happen. If your outer atoms are different, then you're pretty much always going to be a polar molecule, almost regardless of whether there's lone pairs or not on the central atom. And so that's kind of what we see here. This oxygen, by not being a fluorine, it's different. It's kind of like if there was a lone pair there. If there was a lone pair here, then it's just like SF4 that we saw already, and that was polar. So having a different element than the other ones that are on the sulfur here is kind of the same effect. We're going to get a polar molecule at the end of it. All right, two more examples, and then we'll kind of wrap up for today. So methanol, if we want to look at its polarity, right? So when we have these longer chain-like systems, usually carbon and hydrogen are involved. And remember what some of the things we've said before. For these kinds of molecules, carbon-hydrogen bonds are nonpolar. So there's no dipoles for those three bonds. Now, for oxygen compared to carbon and hydrogen, oxygen is more electronegative, right? So that means I do have two polar bonds in this molecule. And they're pointing from the carbon to the oxygen and the hydrogen to the oxygen. But notice they're both kind of pointing at the downward slant, which means when I go to add these two together, I'm going to start here. I have one that's going down to the left, and then I have one that's going down to the right, which means I don't end up where I start, so I do have some sort of net dipole here, which means that my molecule is going to be a polar molecule. And probably more often than not, if you have a single oxygen in a compound that otherwise is all carbons and hydrogens, it is going to be polar to at least some degree. It might not be really polar, but it is going to likely be polar. That's kind of a general quick approximation you can almost always make that carries on even into organic chemistry. So when you start seeing organic molecules that have like carbon, hydrogen, and like one oxygen, they're always going to be polar. But if I have, like in this case, I only have one carbon and some hydrogens here, that's going to be pretty polar because the one oxygen here is going to have some pretty big dipoles and not much else here to kind of take up other space otherwise. But if I have a huge carbon chain on this direction of all carbons and hydrogens, I only have one little polar piece and then the rest of everything is non-polar. And at that point, the whole molecule is less polar because the molecule itself is very big but only has one little polar part. And so that, again, more trends that we'll see kind of pop up down the road in terms of some of the applications of these things. All right then, last example, we'll take a look at our acetate. Right? So for acetate, I actually didn't draw a Vesper sketch on this guy, so this will be a good chance for me to do that. Let's see, let me scroll down some. I'm just going to scroll down below everything here. So for acetate, we want to draw a Vesper sketch of this first. Apologize for not doing that in the proper order earlier. But if we draw this thing's Vesper sketch, remember we have two central atoms. Right? Each of these carbons are effectively central. One is tetrahedral, so I'm going to start by drawing it with kind of a normal tetrahedral arrangement, go into the other carbon, and then this carbon actually has a trigonal planar geometry, right? Because if I scroll back up, that second carbon, here we have three things total around it. We said it was a trigonal planar molecular geometry for that right carbon. So for it, if I want a trigonal planar geometry, I can imagine having something like this. And again, where I put the double or single bond really here really doesn't matter that much. And in terms of my dipoles, carbon-hydrogen bonds, these three bonds are all nonpolar. On my wedge here. Carbon-carbon, these are the same two elements, so this is a nonpolar bond. So what I have is these two dipoles, right? I have one dipole pointing down towards that oxygen, one pointing towards that oxygen. And they're not exactly 90 degrees, although I've kind of drawn them maybe that way. Really, this should be slightly different. So let me angle those maybe a little bit more accurately. This one really should be kind of up to the right some at least. They're more like a 120 degree angle between them. But regardless, if I have one dipole that's kind of going up to the right, one that's going straight down, well, I do have a net dipole here, right? Going from where I started to where I'm ending. So if I have a net dipole, that means that because I have the net dipole, this molecule is polar. Right, that's the conclusion I can draw. That's an arrow that I'm trying to draw there pointing from net dipole down to, because it has a net dipole, it is a polar molecule. And this, again, kind of in line with what I said in the previous example. If we have oxygens on along with a bunch of carbons and hydrogens, more often than not, that molecule is likely polar. It's almost, I'm not going to say it's impossible, but it's unlikely to have oxygens with a bunch of carbons and hydrogens in a way that is going to be nonpolar. It can happen in maybe some really, really extreme circumstances, but for the most part, molecule is going to be likely polar in terms of how we are going to talk about it, and really for the applications then we'll see down the road in terms of what it really means for something to be polar from a property standpoint. And like I said, that's stuff that will come more in 1212. All right, so that's the last example that I have for today. I'm going to kind of cut things off here. Next time what we'll start getting into is kind of the other part of Chapter 9 that looks at bonding theories. So we'll talk about probably valence bond theory first, and take a look at doing some of the valence bond sketches that you guys have probably been seeing and doing a little bit in the lab. And then after that, next Wednesday, we'll be getting into molecular orbital theory, which is kind of something that's very different from everything else that we've seen. It's a totally different way of thinking and talking about bonding that gives us a little bit more kind of information that we don't get always from Lewis structures in particular. So that's kind of where we're heading down the road. As always, if anyone has any questions, comments, concerns, feel free to reach out to myself or either instructors. We'll be happy to help, and we'll see you then next time.